Hey guys, now we're going to look at the situation of when you have a elastic collision between two objects, one dimensional, but you don't know the speed of either object after the collision. So in this situation here, we have like 6 kilograms moving at 10 meters per second to the right, 2 kilograms moving at 20 meters per second to the left. They run into each other, they're going to bounce off. And when you think about it, there's really only one way they can bounce off. There has to be a certain speed for each of them. And we should be able to predict that. And we can predict that, but the math gets a little bit dense. So this is a problem that you will not see on the AP exam. It just takes too long to solve. But you will definitely see it in college. And it's a legit fair game question as far as college physics goes. On the next test, I will have an extra credit question, which is like this. And this video is for if you want to learn how to do it, so you have a head start in college. And also, I'm going to show you an easier way to do it than how they do it in the book, and probably easier than the way they're going to show you how to do it in college. So there's kind of an elegant little shortcut that you can do to do it. So let me illustrate the problem here. Okay, so this is the problem, and this is the hard way to do it. This is the mathematically denser way to do it, but I do want to show it to you because some people actually do find this easier if you're particularly good at math, and this sort of a series doesn't bother you. This works really, really well. But there, like I say, there's an easier visual way to do it. So I'm showing you this to give you a preview and also to show you what I'm saving you from if you like to be saved from this sort of thing. Anyway, so the problem here is we have 2 kilograms moving at 4 meters per second to the right and a 4 kilogram puck moving at 5 meters per second to the left. They're going to come over, they're going to bounce off each other, and they're going to rebound at some speed. We're trying to figure out what those are because we're not given either one. So on this side here, this is the equation you're already familiar with. It's the momentum equation. So this is the momentum of the first object plus the momentum of the second object before the collision, and that has to be equal to the momentum of the first plus the momentum of the second after the collision because momentum is conserved. So we plug in the values here, 2 kilograms, 4 meters per second, 4 kilograms at minus 5 meters per second. I switched the negative signs, but it comes out the same way. But then the result is we have 2 kilograms moving at some speed, V1 after the collision, and 4 kilograms moving at some speed after the collision, which we're calling V2. And we don't know either one. So we have one equation with two unknowns and we're kind of stuck. Anyway, what we do is we go as far as we can with it, and then we wind up defining one of them in terms of the other. So in this example, I've broken it down to V1 is equal to minus -6 minus V2. That's what it all comes down to. You can follow through the algebra on your own. Now, this part is new because as you may recall, in an elastic collision, kinetic energy is conserved just like momentum is. And the expression for kinetic energy is this right here. You can barely read it. 1/2 mv squared. That's how we calculate the kinetic energy of an object. So we calculate the kinetic energy of the first object, add to it the kinetic energy of the second object, and that has to be equal to the kinetic energy of the first plus the kinetic energy of the second after the collision. Because it's an elastic collision, there is a perfect bounce. All kinetic energy is conserved. So again, this is for the before the collision. This is the term for the first object, 1/2 times 2 kilograms times the speed, 4 squared, plus the kinetic energy of the second object, and it equals the kinetic energy of the first plus the kinetic energy of the second after. But again, we don't know the speeds. So again, we define the speeds as V1 and V2 for the speeds of each object after the collision. Again, we have two variables with only one equation, but we do the best we can, and we wind up getting, we simplify as much as we can. In this case, we wind up with 66 equals V1 squared plus 2 times V2 squared. Then, you probably see this coming, we substitute in the value for V1 that we got in this equation for this equation. That's what we've done here. So we have 66 equals V1 squared, so we have this term, quantity squared, plus 2V2. And then we solve it all for V2 because we have one equation with one unknown, and that's awesome. Now, along the way, we have to do the quadratic formula. That just is what happens with these. That's one of the reasons it's a pain in the neck. But when it all boils down, we get to V2 the speed of the second object after the collision is either 1 meter per second or -5 meters per second. There's two possible solutions to this. Then we plug these values into our expression for for V1, and we wind up that V1 comes out to be either -8 or let's see, or 4. -8 or 4 is what it comes out. Yeah, -8 or 4. That's what they are. Now, the interesting thing about this, and this is kind of cool, this system gives us two answers, and the two answers are the speeds before the collision and the speeds after the collision. So here, this is V2, -5. Well, that's how fast it was moving before the collision. It was moving left at 5. And solving this reveals that. And the other one is the speed after the collision. And likewise, when we get the answers for V1, when we substitute them in, we get -8, which is the speed after, because 4, well, that was the speed before the collision. So this is kind of cool. It's all one mathematical series. So computers love this. It's easy to program a computer efficiently to do this sort of thing. That's one of the reasons that this is how they teach it in college physics classes now. Because so much of what we do is translating things into formulas that computers can digest. And they're better at arithmetic than we are, so it worked great. But this is a pain in the neck, and there's an easier way. Now, to show you the easier way, I want to go back to the simulator, the air-track simulators that we had last time. Here we go. All right, and I have this one set up as a mass of 4 moving at 30 meters per second. That's the red one going to the right. And then the other one is a mass of 3 moving at 40 to the left. So 4 at 30 running into 3 at 40. It's set up as an elastic collision, and we're going to run it and watch what happens to the speeds after the collision. Right? They kept the same speed. They just changed direction. They bounced off each other and went back at the same speed at which they came in. All they did was change direction. So that's kind of interesting. How'd you pull that one off? Well, it's because of the numbers that I used. You can see that the momentum for each one is the same. 4 times 30 is the same as 3 times 40. There's 120 units of momentum coming toward each other. And since momentum is conserved, the momentum that a puck carries in has to be carried out. That's the only way to do it. And the only way to keep the same momentum for each piece is for it to keep the same speed, but just change the direction. Okay, so this is a special case of an elastic collision where they bounce away at the same speed that they came in. Now, let me show you how this works. It's easier to see and understand if we do the same thing, but with an inelastic collision. So now they're going to stick. And make a prediction here. What's going to happen when they hit? And the answer is they stop because the momentums are the same. So when they hit and stick, the momentum adds up to 0 and they're not moving. Okay, now what this reveals, and this is not something we've talked about before, thought about before, but the system itself, the system of these two objects, the system has a center of mass. And sometimes the center of mass is moving, and sometimes, like in this case, the center of mass of the system is not moving. The center of mass is right here, and the two pucks are coming in, approaching that, and they run into each other when they both reach the center of mass, because that's the center of mass of the system, and then they bounce away and go back the way they came. And if they don't bounce away, well, they just stop at the center of mass. They are the center of mass now, and they stay put because the center of mass is not moving. Relative to the center of mass, the two objects always come in and go away at the same speeds. They do this thing that I just showed you with the inelastic or with the elastic collision. All bouncing systems do that relative to their system's center of mass. And that's what we take advantage of in the shortcut solution. Okay, now how do we do this? Well, we already know the first step, and that's to find the speed of the center of mass. And the speed of the center of mass is how fast the two objects are going to move if they stick together. If they're stuck together, they have to be moving at the speed of the center of mass because they are the center of mass. Okay, and just to review, the way we do that is we take the momentum of the first, 4 times 30, plus the momentum of the second, 3 times negative 40. And we set that equal to the total mass, which is going to be 4 plus 3, times the speed of the center of mass, the final speed. And in this case, we have 120 minus 120, so 0 equals 7 times VF. So the center of mass, in the example that I was showing you on the simulators just now, the speed of the center of mass is 0. Okay, so for the easy solution here, the shortcut solution for our difficult problem, the first step is to find the speed of the center of mass. And we do that by just doing the inelastic equation thing. So we have 2 kilograms times 4 plus 4 kilograms times negative 5 is equal to the total mass, which is 6, times the speed of the center of mass. This comes out to be 8 minus 20, which is minus 12, which equals 6 times the speed of the center of mass. So the speed of the center of mass equals negative 2 meters per second. Okay? We figured out that the speed of the center of mass of this system is 2 meters per second, and it's moving to the left. That kind of makes sense. This is a bigger object, and it's moving faster, so it makes sense that it would dominate, and the center of mass of the whole system is going to be tracking to the left. So that's the first step. The second step is to figure out how fast each of our objects are, object 1 and object 2, how fast they are moving relative to the center of mass. So the center of mass is moving at 2 meters per second that away. The first object here was moving at 4 that away, and the second one was moving at 5 this away. These two are moving toward each other. So the speed of this one relative to this one is going to be 6. That's going to be the closing speed, if you will. Whereas this one is trying to catch up to the center of mass, so its speed relative to the center of mass is 3 meters per second. Okay? Now, they're coming toward each other, they're going to collide, and they're going to move away from the center of mass at the same speed that they were moving in. So after the collision, this was before, after the collision, the first was moving away from the center of mass at 6, and the other one is moving away from the center of mass at 3. And again, that is relative to the center of mass. So the last step, or the next step, I should say, is to figure out the speed relative to the ground. Okay, V relative to the ground. And again, the center of mass is going 2 meters per second this way. And the first object is moving away from this at 6, but it itself is moving. So the relative to the ground, this is going to be moving 8, right? So this is moving away from this, but this itself is moving to the left. So we got to add those together. And we get 8 meters per second for the first object after the collision. The other object is moving away from the center of mass, but the center of mass is moving to the left, and this was going away. So it's kind of like walking the wrong way on a treadmill. So it's moving at 1 meter per second this way, relative to the ground. So these speeds are relative to the ground. Okay, and that's it. That's it. That's the answer. We bring this back here just as a reminder. We saw that our final speeds were 8 meters per second, or negative 8 meters per second and 1 meter per second. And that's what we got. Negative 8 meters per second moving that way and 1 meter per second moving that way. Right. Now, this requires a little bit of visualization. You might want to play with it a little bit, kind of move your fingers back and forth and see how it works. But you do this a couple of times, it actually makes a lot of sense. The arithmetic on it is very simple. The only algebra you have to do is just to figure out the speed of the center of the mass. And after that, it's just very simple addition and subtraction. Okay, I hope that's helpful. Like I say, that's going to be an extra credit question that will not affect your grade, but it is a neat trick that you will be able to use when you get to college. It's a good one for your bag of tricks. Okay, that's it. We will see you next time.